Recording first. So, hi and welcome everyone to today's talk. We are hosting Professor Howard Stone, who is a professor in mechanical and aerospace engineering at Princeton University. He's a fellow of the American Physical Society. He is the past chair of the Division of Fluid Dynamics of APS, and he was the first recipient of the Bachelor Prize in Fluid Dynamics. He has been
You can
elected.
you can stop now. You can stop now.
I will. Thank
Yeah,
you.
you
I
don't
will
have.
leave the rest to him. We are
Yeah,
very excited to hear about this talk. So, yes, I'll leave it all to you. Thank you.
yeah, thank you. I didn't mean to be rude, but it's okay.
No, it's
Um,
okay.
so first, thank you to Azada and Aman for the invitation, and thank you for those who are able to listen. It's a pleasure to join you by Zoom from some miles away. So I have a talk I'm going to give that um, has a few themes that might be of interest, and so let's get started. So I want to just thank my group. This is my group, and there are significant others just before COVID hit. And this was my group and a few of their family members when two of my students graduated with their PhDs in December. And as most of you know, if I have any useful ideas to share, it's because of the community that we have in research. Okay, so I'm going to tell you a few things about just glimpses at a couple fluid mechanics problems that we've worked on over in recent years. And then I'm going to focus on some problems involving self-similarity, which is an idea I like as a sort of organizing principle to connect an experiment and a model. And at the end, if there's time, I'm going to show you a problem of surfactant spreading, which leads to equation some of you might have seen called Berger's equation. And again, we focused on a self-similar feature. So I'll kind of dance through some of these topics. So to begin with, a couple fluid mechanics problems. I tell the story this way: when COVID hit in March 2020, right, we all went home. We were locked at home, and it turned out at about March 1st, 2020, a colleague from France had come to the United States to work with me. His name is Manu Kapkarian. He's an expert on blood flow, an experimentalist. And 10 days after he arrived, he uh, was isolated at home in Princeton with his family. And we started to talk every day. And we were talking about all the reports of people getting sick in public places. And we got interested in this idea of airborne transmission. And now we know a lot about this. Of course, we've all heard a lot about it. And of course, in the fluid mechanics world, there's been a lot of work on droplets. I'm not going to say anything about droplets. I'm just going to ask the question, when you speak to someone, how much of what you speak travels far enough to uh, cover their head if you were sitting near someone? And we got permission when the university was closed. We got permission to go back to the lab, and Manuk in the lab started to image what happens when you speak. Uh, to a first approximation, there is only one paper in the entire fluid mechanics literature that says anything about speech and sound and uh, consonants. There's one paper about the letter P, what happens when you pronounce P. I'm not talking about acoustics. I'm talking about the airflows that are created by sound. If you look at the movie playing, you might be able to see the speaker on the right side. This is imaged in a lab that's dark. It's filled with a aerosol that's created by a fog machine, and then a laser sheet illuminates a plane in front of the speaker. And so when he speaks, what you can pick up the velocities by tracking what takes place when small aerosol droplets intersect the laser sheet. I'm just going to play it once more and just notice the following things that you might not have realized. The time in the upper left is in milliseconds. The horizontal distance is about a meter. And you're going to see that when the speaker talks, here he's saying what are called, a linguist called plosives, the letter P. He's saying, Peter Piper picked a peck. You'll see that within 1 to 2 seconds, the air from his mouth has covered a distance nearly a meter. You might find this interesting because the World Health Organization's social distancing guideline for more than a year was a meter. In the United States, it was 2. So we ended up doing lots of studies of this, including some numerical simulations, and ended up concluding that in ordinary speech, if you time average, you get an image a lot like the one on the left, which is effectively that of a turbulent jet to a good approximation. It has the angle of a turbulent jet. It has some of the typical flow structures. And the Reynolds numbers are, a few thousand, depending on the flow rate you produce and how loud you're trying to talk. We wrote a few papers on this. We also wrote about masks, not again about droplets, but about how masks change the so-called respiratory jets. And then in recent years, we've been trying to study more about the connection of fluid mechanics and speech. In other words, how you make sounds and the airflows associated with them. And in order to do this, we've looked at MRI images that show you how your tongue and jaw and lips and teeth move to control the cavity that's available for the airflow. We have looked at this. You can find this in different languages. And because when the air leaves your mouth, your lips and your teeth are like the orifice of a pipe. We've tried to understand how that changes the restrictions of the flow. And the consequence of this is we tried to now make a fluid mechanics-like model that links the features of language to the air flows that you create in front of you, the respiratory jets. If you're all listening, just try to do this. Say the sound P, and you'll notice that when you say the sound P, your lips are shut momentarily. And what that's doing, of course, is you're trying to speak, you close your mouth, the pressure builds up in your oral cavity, and then when you open your lips, you get a very strong airflow. So there are fluid mechanical features associated with this, and we've then now coupled this to a Navier-Stokes solver where if you look in the lower left, we have a model of your teeth and lips moving. That's the cavity. That's the orifice of the cavity. We measure the airflow experimentally in the lab associated with different phrases, and then we couple the airflow, that's the input to a Navier-Stokes solver, and then it's color-coded here by speed and vorticity. And so you can see the kind of features that now we're trying to understand to link fluid mechanics of kind of the air around you when you're having an ordinary conversation. And after now a couple of years, we're trying now to draft a paper that tells this fluid mechanics story. Anyways, I thought you might be interested if you hadn't seen that yet. Here's a second problem. It's completely different, but it's something we worked on a few years ago that I've always found very interesting. When you look at this, you're going to think this is the most boring thing you could possibly study, and I'm going to try to convince you, one, that that's not true, and two, that we discovered something new that no one had ever seen in the Navier-Stokes equations before. So this is a fluid flow at a T-junction. I show you at the bottom of the slide, if you can see my cursor, different cases where you see a T-like shape of a pipe, whether it's industrial machining, a laboratory device, or in physiology. There are lots of connectivity. And I'm going to tell you about a problem where the flow comes in at the top of the T and goes out at the sides of the T. The problem I'm going to tell you about here has a modest Reynolds number. It's typically of the order of a few hundred to a few thousand. So inertia dominates, but it's not completely a turbulent flow. Okay, so if you teach fluid mechanics, this is chapters 6 or 7 in an undergraduate fluid mechanics book will be flow in pipes. And flows like this have been studied experimentally and numerically for decades, both in industry and in academics. And to a first approximation, I'm going to suggest that everyone missed the most interesting thing about the flow. Now, to give you an indication about the flow, this is the experimental configuration we were first studying. It's a T-like shape with flow in at the top and out at the sides. The Reynolds number is defined just like you'd ordinarily define it. And if you do this kind of experiment and study small glass beads in a fluid like water, nothing terribly interesting happens. I should say we were first doing this because a colleague was interested in how much energy a particle would hit the wall with and whether or not it might damage an oxide layer on a pipe, for example. But what you see is the particles come in at the top, they leave at the sides. They typically are, you can imagine, are overshooting streamlines because they have a different density than the fluid, and they have a somewhat complicated trajectory, but not too complicated. And anything that comes in leaves. And one day when we were doing this experiment, air got trapped in the flow. So I'm now going to show you what I believe had never been observed in the fluid mechanics literature before for this configuration. All the dots are gas bubbles. They have obviously are less dense than water. The orientation of the pipe, though, doesn't matter. Gravity plays no role in this effect, but density difference does. And in this case, the flow comes in at the top and out at the sides. And when you film this with a high-speed video, what you'll start to observe is that bubbles are accumulating in the middle of the pipe. If you ever tried to sketch this flow, if you see my hands, if you tried to sketch this flow and someone were to ask you, what do you think the streamline structure is? Are the streamlines sort of a stable or an unstable kind of configuration from the standpoint of nonlinear dynamics? Most people would say, well, since everything is going away from the middle, shouldn't the middle be an unstable stagnation point? That's a reasonable thought, but you can see the experiment, at least when the Reynolds number, which is here a few hundred, I think around 500, you can see that something's causing the bubbles to accumulate. And so that's the story I'm now going to just briefly tell you about that we studied experimentally and numerically. We went about this at one point by just doing numerical simulations. Here you'll see the numerical simulation systematically changing the Reynolds number. The yellow just means regions of high vorticity as calculated with the so-called Q criteria. Not surprisingly, when you increase the Reynolds number, the flow gets more complicated. If you're familiar with what's called the Dean flow, or a Gortler-like flow, when the flow has to turn a corner, it starts to generate vorticity, so the streamlines start to curve. And they get progressively more complicated as the Reynolds number increases. Okay, so now you can explain one thing about the movie I just showed. Because you have vorticity, if you study turbulence, you know that bubbles go to the center of vortex lines. So you could imagine that if there were bubbles in this flow and you're generating vorticity, that bubbles would go to the middle. And actually, I can show you one thing quickly. If you look at the bottom slide, the bottom right, you see essentially two vortices on each side. Around the center, then there's sort of four features. And you see the four features in this movie because if you look hard, you could probably count that there's sort of two strings and with going to either side, and you see them fluctuating a little. So the bubbles are getting trapped in a vortex, but what's the thing that's keeping them from leaving? Why are they getting confined to the middle? And that feature is because at a critical Reynolds number in this flow, the flow changes its topology like this. In this flow, for a 90-degree angle and a square cross-section at a Reynolds number 590, if you were to try to trace a streamline, what you discover is there's an internal stagnation point. So the flow is coming, the streamline is spinning to go out like a vortex. It reaches a finite position where the velocity is zero, and then it comes running back down the middle. And in the fluid mechanical terms, this feature is called vortex breakdown. And the region of trapped flow is called a vortex breakdown bubble. And I could say more about how we stumbled on this, but effectively, this region of trapped streamlines is the region why bubbles are getting trapped and confined to the center of the pipe, so long as the Reynolds number exceeds this critical number. And I believe we are the kind of had stumbled on this idea that you can have vortex breakdown phenomena in these confined configurations. To illustrate this streamline structure, I'll show you a video. We got lucky one day, and here you can see the bubbles coming in at the top. They're going out at the sides. You can see them spinning around and going out on the outside, and then you can see them running back the middle. So this sort of illustrates this three-dimensional flow with this vortex breakdown phenomena inside a pipe with a pretty modest Reynolds number. When the flow gets more complicated, we still see some structures of it, but the turbulence would eventually ruin it. Okay, so if you're paying attention, I can now ask you a quiz. Suppose now I give you this geometry, but it's filled with dirty water, and then I want to turn on clean water and clean out the pipe. And you were to ask yourself, or you ask your students, how long does it take when you turn on the pipe to clean the flow? So here we turn on fresh water, and what you see is most of the flow cleans quickly, but where you have the vortex breakdown structure, it takes longer for the fluid to get out because those are regions of trapped streamlines, and the only way dye can get out is by diffusion, not advection. So anyways, we've written a number of papers on this. I freely say in public, I was never able to get a grant. I tried for 4 years, and I eventually turned to something else. But I always found this problem interesting, and so I like to share it with people. Are we doing okay, Azada, Aman? Is it okay so far? Okay, no, well, at least you guys aren't asleep yet. So, okay, we're doing okay, maybe. Okay, so the main part of the talk is I want to tell you something involving self-similarity. And when you teach fluid mechanics, of course, you teach self-similarity, but you teach it in sort of kind of model problems. And so I'm going to show you how it comes up in some research problems. The first one I'm going to show you was work I did with my graduate student, Katie Wu, and Camille Duprat, who's a professor at École Polytechnique in Paris. And the paper just appeared. If you were to ask someone, how do you think about self-similarity if you just meet a person on the street? You might show them similar triangles and try to focus on the geometric similarity of objects. But in fluid mechanics, the way we generally run across it, or in heat transfer, is we describe some kind of diffusion problem. Here I've just sketched, you have some concentration C, you're solving a linear diffusion equation. You imagine the concentration being some specified number C naught, say at a wall, and then it's going to diffuse into a domain with no chemical. If I were to teach this before I did any math, I would make the sketch on the left, which is to sketch the concentration profiles at different times. And of course, self-similarity then is the idea that all these different solution curves at different times collapse to one universal curve if you plot x divided by the square root of time, or square root of dt, where d is a diffusion constant. And this is the kind of thing that you teach or you took in class when you're a student. And it has the feature that you started with a math problem with two independent variables, x and t. And self-similarity is essentially taking the so-called partial differential equation problem and making it an ordinary differential equation problem. So the first example I'm going to show you is a problem just like this with two variables, but it's a little more complicated. And then I'm going to show you one with three variables, which is a lot more complicated, but then I'm going to show you a miracle happens. Well, at least a fluid mechanical miracle. If you're interested, by the way, in a couple nice papers that talk pretty generally about self-similarity as it occurs in fluid mechanics, I put two references on the slide. Okay, so the way this comes up in fluid mechanics, and I'll show you sort of how this comes up, at least in laminar fluid mechanics, and maybe there's examples in turbulence, is not just the linear diffusion equation, but diffusion-like equations. So they involve two space derivatives on the right, but in the place of the diffusion coefficient, you can have a nonlinearity, like here, c cubed. I'm going to show you that this equation basically comes up in a large range of so-called thin film flows. Now, if you have a diffusion-like equation, even a nonlinear one, they often allow similarity solutions. By similarity solutions, I mean that the function you're looking for is time to a power, alpha, times some function, capital C, of a ratio of two independent variables, x over t to the beta. That's sort of what you often teach. That idea, of course, is useful if you can identify alpha and beta. And normally you need not only the equation, but you need boundary conditions to do that. And if you succeed in this, then the partial differential equation becomes a nonlinear ordinary differential equation, so you can normally quickly solve that numerically, so long as you have boundary conditions. And what you'd like to do is compare with experiments. So I'm going to show you a few examples of things like that. The right-hand side of the screen is empty because I'm going to fill it in later. The left-hand side of the screen is really what you took as a student. If you took a course in fluid mechanics, you would have seen an example or two like this, or if you've taught, you would have taught an example or two like this, though normally we teach the linear problem. Okay, a very nice example of this is a paper Herbert Huppert wrote 40 years ago, where you just take a syrup, like something you put on pancakes or a plate, you put a viscous fluid and you watch it spread. When it spreads, you measure radius versus time. Don't worry that the axes are messy. The vertical is the radius, the horizontal is time, the axes are log, and it turns out all his data falls on a straight line on this log plot. The slope of the straight line is 1 divided by 8. In many laminar flow problems, are very clean exponents you can obtain. And the nice thing about the experiment, if you look at the horizontal axis, is he took data over long times, 1 hour, 1 day, 1 week, almost out to a month. So it's very robust phenomenon. There are many problems that involve thin films. They can be rivulets or whatever. So there are a wide range of examples where you see these thin film structures. One problem that I worked on a few years ago, which I liked, I didn't know much elasticity. I wanted to learn something about elasticity so I could do more fluid structure interaction problems. And so we coupled this idea of a thin film with the most sort of famous solid mechanics problem, which is the bending of a beam. And here's, you can see a video playing that when the fluid loads the beam bends. And there are two images here. There's a side view on the top, and the bottom is a top view. So as the fluid flows, it's a so-called gravity current, like I just showed you on the previous slide, but its speed is dependent on the deflection of the beam, and so these two problems are coupled. And if the beam is very soft, the bending happens very rapidly, and then there's a much stronger coupling of the motion of the fluid to the bending of the beam. And I worked on this with my postdoc, Hyung-Soo Kim, and Peter Howell in Oxford then did a very beautiful analysis coupling these two problems together in a very elegant way. Okay, so why do these equations, why do the Navier-Stokes equations lead to a structure that you can analyze analytically? I'm going to try and show you that here. For this audience, I don't have to explain the Navier-Stokes equations. I'm using U for velocity, rho for density, mu for viscosity. And of course, you could try to solve these problems numerically, but many of these thin film problems, they're moving boundary problems, so they're changing shape. They might not be so simple. But when a film is thin, and by thin I mean that if h tells you the shape function, then its gradient is a small number. In other words, the shape changes, but only slowly along the flow direction. And when that's true, you don't solve the continuity equation in its normal form. You solve it in the form almost like you do in gas dynamics. You write it as like a conservation law for the height. And this is an asymptotically exact description of the continuity equation, where I'm using the divergence with the perpendicular symbol to just measure variations along the flow. Okay, so this continuity equation or volume conservation equation couples the height to the velocity. How do you get the velocity? You turn to the Navier-Stokes equations. And since the film is thin and often the viscous fluids move slowly, you assume the Reynolds number is low, so you neglect inertia. And then you use what's called Darcy's law. You replace the viscous term by a term proportional to the local velocity divided by the height squared. And as soon as you do that, you can integrate this equation to get the pressure and apply boundary conditions. And when you take this velocity field and substitute it into the continuity equation after a couple steps involving integrating for the pressure, you get the equation shown at the bottom. You can recognize the continuity equation in it. There's a d by dt on the left where my pointer is. There's a divergence of a whole bunch of stuff, which is the mass flux or volume flux on the right. The equation involves the viscosity, and in problems that have a a film to them. There's gravity that enters two terms. It enters two terms because you can have a film spreading on a horizontal plane, or you can incline the plane and get a component of gravity along the plane. Those are the two gravity terms. And because the film is curved, you have a surface tension term. And you notice it's a scalar PDE. There's one unknown, the height. That's the only thing now you have left to solve for. But it's nonlinear. It has this h cubed sitting over here like a diffusion coefficient. It has 4 derivatives where it has surface tension. It has 2 derivatives where it has gravity. So it's still complicated, but it's now only a scalar equation. It's not coupled nonlinear PDEs. It's one nonlinear, in this case, fourth order PDE. Maybe that's helpful for you to see why this is such a useful thing. It has many different features to it. Okay, so the problem we were interested in is shown on the right. If you take a cylinder and push it up against the plane, as you see on the right, we're then going to place a small amount of fluid at the bottom. And if the fluid wets the surface, what it does is it climbs up the narrow wedge between the cylinder and the plane. And I've sketched that here in cross section. And so what you see when you do an experiment like this, when you look at it from the front, if you put a little fluorescent dyed liquid in the bottom, it's going to wet the plane, and it climbs up the narrow wedge between the cylinder and the plane. And what was, I think, first pointed out by a paper by Tang and Tang, and then really documented beautifully in a paper from David Curé's group, is that it turns out the fluid rises at a certain rate. That's a power law of time. In fact, it rises as t to the 1/3. And you might be surprised, but unless you put in some other physical effects, the theory will claim that it just keeps going up and just rises higher and higher, though slower and slower, filling very narrow wedges. And so this you'd call a power law. And so I'll explain where the t to the 1/3 comes from. But if you really want to see a beautiful argument, read the 2011 paper from David Curé's group. And to a first approximation, there was not a complete analysis of this problem. There are variations of an analysis in the top 2 papers I mentioned, and a nice analysis using a PDE approach by Massou Adoy and colleagues. But the question we asked was, everyone described this problem as universal. And the universality they were saying was because it always looks like t to the 1/3. In fact, it doesn't matter what the shape of the cylinder is. If you use sort of a flattened cylinder, it still rises as t to the 1/3. So the suggestion was that this problem is universal. But the question we wanted to ask is the prefactor that is going to come into this, is it also universal? Does it know anything about geometry? So that's what I'm now going to show you, what we looked at experimentally and with a model. Okay, so this is the geometry. It's a little, you have to think about it for a while. On the right, we want to describe how things are rising in the vertical direction, opposite gravity. And in the middle of the slide, we want to describe how the fluid is filling this wedge-shaped region between the cylinder and the plane. This wedge-shaped region has a radius of curvature we're going to call S. And we did, experiments with different radius cylinders. We did experiments with different liquids. And I'll compare those with the experiment we did. But there are other people who had also done these experiments. Okay, so there's sort of a 3-dimensional view of what you might see when you look in the wedge. And we're now going to describe the geometry either between a cylinder and a plane or between 2 cylinders that might have different radii. And so what we're going to say is that if h is the vertical height of the width of this liquid section, it's a power law of the horizontal dimension because the wedge is narrow. So you can get away with that. And different geometries are characterized by this number n. If it was a cylinder near a plane, n would be 2. If it's a soft cylinder that you squeeze near a plane, n is 3/2. So n can take on different numbers. And the key parameter, which brings in the geometry of whatever you're set up in your experiment, is this number c. C has funny dimensions because it's tied to what you choose for n. But c is a characteristic, a geometric characteristic that tells you what the typical fluid profile is in this gap. Is that okay? Sort of? Okay, and the other number you need is the radius of curvature S that separates the liquid colored gray from the air outside. And you can see that because of the way the liquid, because it's a wetting liquid, the meniscus is curved. So in this gray region, the pressure in the liquid is low. That's why the fluid is climbing higher, because it has a lower pressure than atmospheric pressure if the fluid's wetting. Okay, so I showed you these kind of continuity-like equations. So when you write this equation for the radius of curvature S that I showed you on the previous slide, when you write this equation that has a time derivative and a derivative of a flux, you get an equation shown on the slide. The equation has two terms in this bracket. One comes from gravity because the column is going vertically, and one comes from surface tension. So this ds dz is from surface tension. The funny powers of n are because we've allowed for a funny shape, height being x to the n. And if the fluid had a certain wetting angle, you'd put a cosine theta in here. We're going to take theta nearly 0, so you can ignore that. But you see surface tension and viscosity, and you see geometry enters in n. Okay, so this equation is terribly complicated. Aman does numerics. If you were to study this problem, you might want to do this numerically. But because it's this feature of a nonlinear diffusion equation, what I'm not going to show you is you can actually find an analytical solution to it. But several had pointed this out. Okay, so because there are dimensions here, I should say LCG is the so-called capillary length. The first thing you should do is make this non-dimensional. So if this conservation equation, which is really continuity equation, if you I should say that the number C isn't anywhere here. The only role of geometry is n. And when you make everything non-dimensional using a length scale, which is the so-called capillary length, and time that just comes from a convenient choice involving surface tension divided by viscosity and a length scale, it turns out that this equation, all the parameters disappear from this equation. So if S tilde is a non-dimensional radius of curvature, all the parameters now are gone from this problem. And the only thing that tells you about geometry is the number n. And this is the first hint that the solution to this problem simply cannot be universal, simply because you have to tell me n. Okay, so this nonlinear PDE, it turns out, has a similarity solution. That's not obvious, but it's true. And a very nice physical argument was given by David Curie. But this equation, if you look at it for a little while and balance the three terms, we're taught to balance different terms. If you balance these two on the right, you'd see that S varies as 1 over Z. And then if you balance the first term and the second term, you'd find out that Z cubed goes like T. And the consequence of that is there's a similarity solution that says the radius of curvature S is time to the minus 1/3 times a function of a similarity variable. And you get an ODE for this function phi. Ignore the complication. I wrote the whole thing out, but you get an ODE, and you can solve the ODE with boundary conditions, but you have to tell someone the number n. So the number n, which tells you about geometry, is needed to work this problem out. Okay, so we did some experiments. We measured the rise height z for different times for 2 different cylinders and 2 different viscosity fluids. They don't vary a lot, but they vary somewhat. We claim there's a similarity solution that others have had. So if you scale the variables z and t, like I showed you, all the experimental curves roughly collapse. And the black curve is the similarity solution with slope t to the 1/3. And you can get everything quantitatively if you determine this prefactor. This prefactor eta star can be calculated numerically. And here we did it for the case n is 2. And the moral of this story is now you can do everything, but you always have to tell someone geometry. But the feature that makes this problem nearly universal is the fact that this prefactor that here is called eta star is only a very weak function of n. And that might be a little surprising, but that's the way it all worked out. Okay, so that's my first example of a similarity problem. And maybe I'll just remind you that what I tried to describe was this beautiful experimental image for how things happen when you're wetting narrow wedges. Okay, Azada, Aman, that's okay? Sort of? Anybody there?
Yes, yep,
That's all right.
good.
Well, you guys invited me, so you can always disinvite me, I suppose. Okay, so this other problem is something is one I also very much like. It's a little different, but maybe you'll find it interesting because it starts with an experiment that other people might have done, but they hadn't noticed, and it ends with a similarity solution. So I showed you this slide already, which is what you see when you teach or take classes where people introduce the idea of self-similarity to you. I'm now going to ask not about equations or physical problems that have two independent variables, x and t. I'm going to ask, what if there are three variables? And the question is it possible that you can find a similarity solution, a non-trivial similarity solution? If you could, then you'd only have an ordinary differential equation. And I'm searching for examples of this. I'm going to show you one that begins with an experiment. Okay, and that problem goes like this. You take a plane, you put some fluid on it, and you watch the fluid drain. In this kind of problem, you imagine that the top point, which is a so-called contact line, is fixed. And when the fluid drains, it just gets thinner and thinner. And this is a problem where the film height h varies with vertical distance x and time. So it really is described by a fluid mechanics problem, and it was first studied 90 years ago by this man, Harold Jeffreys, who wrote down a variant of the equation I showed you before. There's a dH/dt term, and because the film is vertical, if you ignore surface tension, the gravity term has this feature. Now, if you took a math class and someone told you that you had a first order nonlinear partial differential equation, they would teach you how to solve this problem by the method of characteristics. What I'm going to just show you is that the scaling idea, if you allow yourself to be a little sloppy, you can solve this equation with algebra. And the way you do that is forget the derivatives and just write the first term as h divided by t and the other term as h cubed divided by x. If you do that and then cancel an h, you see that h squared is proportional to x divided by t. And in fact, that's an exact solution to this problem. As Jeffrey pointed out, this ratio of the square root of x divided by t, and I put in the right physical factors that come from the equation, this is an exact solution to this differential equation. It won't satisfy initial conditions, but it satisfies the equation. And it says that for any fixed position x, as time goes forward, the film should get thinner and thinner and thinner as time runs forward, as you're draining fluid. Okay, this is the Jeffrey problem. Here's an experiment that shows this feature. You take a glass slide in the lab, you wet it with dyed water, and you hold it vertically and you watch it drain. And what you see is that the dye color gets less and less as you lose fluid. If I were to ask you what the most interesting feature, someone has to answer this question, by the way. What's the most interesting feature you see in this experiment? What would you say?
The intensity on the sides, maybe?
Yeah, it's the feature of the sides. There's an edge effect. Okay, that edge effect I'm going to show you is effectively a boundary layer, just like we study in fluid mechanics. But to a first approximation, for 90 years, the fluid mechanics community has only studied the middle of the film because Jeffrey studied a uniform film. And so if you look only in the middle of the film, that's the problem Jeffrey studied. In the middle of the film is uniform and just getting thinner. But near the edges, there's a more complicated shape. And so the way we studied that is with interferometry. This is work done with my former graduate student, Nan Sue. So this is looking at the film using interferometry. So the distance between fringes tells you a change in film thickness. There's an edge effect on the left where the film is curved, so the light it gets refracted easily, it's dark. And the middle of the film, which is toward the right of this picture, is nearly uniform. To just show you what the Jeffrey solution does is if you measure the film thickness in the middle of the film, you can imagine standing at different locations that I'm going to call X and measuring the film height as a function of time. And if you do that, you get these kind of curves, film height H versus time. There are 6 curves here because we look at 3 different positions and we also use 2 different viscosities, okay? These are film thickness versus time in the middle of the film. These are 6 different curves. Jeffries claims that the solution should follow the similarity solution shown at the top, okay? So if you take the film height and scale it by the Jeffries solution, these curves become a universal curve, okay? And that's the idea of self-similarity again, okay? That things can be self-similar. Okay, but now I'm not interested in the middle of the film. You're going to say, that's boring. What about the edge of the film? So let's look at the edge of the film. Okay, so if you look at the edge of the film, what we're going to do is, instead of walking in the vertical, we're first going to just pick an X and walk in the horizontal, okay? So we're going to pick an X, we're going to walk in the horizontal and measure the film height at a given time. And if you do that, it looks like this. Here's the film height versus the horizontal dimension at a given time at this location X. And you see the film is a little thicker near the edge than in the middle. And in the middle, it's trying to do the Jeffrey problem. Now we're going to pick 2 different X's. So now there are 3 curves. And then we're going to change the fluid viscosity and we're going to make measurements at different times. Okay, so now we have data for 2 different viscosities, 3 different times, 3 different X's. There are 12 curves on this graph. And then the question we asked is, are these curves related? Do they have something about them that is always the same? Okay. And so that's now what I'm going to show you, that these curves, in fact, have something in common. What's unusual about this is, of course, there's a surface tension, there's gravity, density, viscosity, but there's film height versus the horizontal distance, the vertical distance, and time. So there are 3 independent variables, X, Y, and T, okay? And 3 physical variables, viscosity, density, surface tension. Okay, so if you only knew this one equation that came from thin film hydrodynamics, and not sure there's something exactly like it in turbulence, but you can imagine there might be if they're thin regions. The first thing you say is what Aman said before, the edge is sort of like a boundary layer. So if you look back at this movie, I'm probably not going to do the last part. If you look back at this movie, the edges are like boundary layers, okay? And the boundary layer is in the horizontal dimension. It's narrow in the Y direction. So you take this equation and you say, look at the highest derivative term. Oh, you first say it's a vertical plate, so you get rid of one of the gravity terms. Then you look at the highest derivative term, and you say the only derivative that matters is not both X and Y. You don't care about the vertical. The boundary layer is changing quickly in the Y direction. So you replace the derivatives by only the Y derivatives, okay? And this other term, you only keep, it's in the gravity direction, so it's only in the X direction. So when you have this kind of shape and you study the thin film equation, you have an equation that has the feature I showed you before. It has a viscous term on the left, a surface tension term on the second term, and a gravity drainage term. The first and the last are what are called the Jeffrey problem. That's what I already showed you. This other term brings in the edge. It brings in the edge as a boundary layer. This is a terrible equation, right? It's got nonlinear terms everywhere. It's got 4 derivatives. It's got 3 independent variables. And the miracle is there's an exact solution to this problem. Okay, that's the miracle. And I could show you how you think about it. But the miracle is you think about it almost like you do the Blasius boundary layer. You say, I'm going to look for a solution H. I'm going to make it look like what happens far away. Far away, you have the Jeffrey solution, which is this x over square root of t. And then I'm going to look for a function of a similarity variable where the similarity variable involves x, t, and y. And you need to define these coefficients. And by substituting into the PDE, you can find the coefficients exactly. It has this crazy form that involves t to the 1/8, y, x divided x to the 3/8. It involves all the physical variables. And this nonlinear PDE becomes an ODE, which you can solve numerically. This similarity variable, I'm now going to use to show you how well it does in comparing with the experiment. And I could talk later about how you sort of by balancing arguments that you sometimes do in class when you make order of magnitude balancing, you could identify this term. Okay, so to just show you how this works, I just showed you this data with 12 different curves when you have film height versus horizontal position for different times and different properties. If you now do what I said, which is scale the height by the Jeffreys solution, which is this x over square root of t, and scale the horizontal dimension by the similarity variable, all the data collapses to one curve, and a numerical solution to an ODE roughly gets the feature of the data. And so this is one of the few examples I know where you have a problem with 3 independent variables, but somehow miraculously you can find a solution. And because it has an edge, I've been asking lots of people over the last couple of years, are there other problems with the corner where you might have this kind of structure in some other fluid mechanics like problems, because it was the edge that made this possible. Okay, I have a few minutes, so maybe I'll just do one more thing for you. Well, I want to mention, if you're interested in this class of problems, Stephen Wilson in Scotland has a nice paper also showing this kind of idea. But in the interest of time, maybe I'll just show you one feature to just start this last topic. And we have a paper that is under review right now, and it's long and detailed. And if you're interested, I could share that with you. But it's the idea of surfactant spreading, and it's work done with my postdoc, Fernando Temprano-Coleto. And it has a small feature to it that I think maybe you'll find interesting. So you might have done experiments where you put surfactant on water and you watch it, the interface move if you put some soap on it. So here's a experiment from the Paris group. You put a little soap on the interface of water and it rapidly spreads out. Why? Because surfactant lowers surface tension, so the high tension far away is pulling the film out. It's this beautiful example of how surface effects create flows. Okay, so what we're going to ask is, how do you analyze a problem like that? And we're going to do it in one limit that hadn't been studied as far as we know, or at least, well, it had been studied not quite the way we had done it. Okay, so these kind of problems come up lots of places. If you're interested and you can't remember the slide I'm sending to you, there's some very nice papers by Oliver Jensen and Jim Grotberg, motivated by a medical problem, which is premature children have trouble breathing, and doctors have them inhale small aerosol droplets containing surfactant, which lowers the surface tension of the liquid lining their lungs and allows them to open the alveoli of their lungs and breathe. It's called surfactant replacement therapy. And there's some very beautiful fluid mechanics problems that Oliver Jensen and Jim Grotberg and others have solved. Okay, so the problems they had solved were on thin films. I'm going to show you a problem with a deep fluid layer, and that had previously been studied at high Reynolds numbers in some past papers. I'm going to show you a low Reynolds number problem on a deep film. And so the problem is sketched at the right. You have a surfactant on the surface, which creates surface tension variations. That drives the flow. The film is deep. And there are typical length scales associated with this, which is like whatever the length scale is that sets your original surfactant distribution. And gamma is the term in physical chemistry for the number of molecules per unit area. It's a surface concentration. If you want to solve this problem, I'm going to assume the interface stays flat. That means there's a dimensionless parameter, the capillary number, that has to be small. And I'm going to assume the Reynolds number is small because that's the limit we decided we'd look at. And if you want to solve for how the surfactant is spread on the interface, you have to solve a convective diffusion equation where D is the diffusion constant of the surfactant and US is the surface velocity, which you don't know. But what you can do is analyze the fluid mechanics equations, in this case, the Stokes equations. And this was first done about 20 years ago, 25 years ago by a man named Thess, who pointed out that the surface velocity U sub S is an integral of the surfactant concentration. That integral is called the Hilbert transform, but the analytical solution to the low Reynolds number problem that links U to gamma is shown here. And so these are coupled non-local equations. Non-local because to get U, you need the entire integral of gamma. Okay, so this is a complicated problem to solve. And what happened a few years ago was a big surprise, which was Darren Crowdy showed that this coupled non-local, nonlinear problem, it turns out if you make a change of variables, if you introduce a complex number, psi, which is the velocity plus or minus I times gamma, Darren chose plus, we've now done plus, but we originally did minus. Mathematically, they're the same for this problem. If you introduce this complex function, it turns out these two equations become the Burger's equation for psi. It's sort of miraculous. It looks like a local equation. It's exactly the feature of Burger's equation. It has one non-dimensional parameter, which is a Peckley number. And the real part of psi tells you the surface velocity, and the imaginary part of psi tells you the surface concentration. Okay, so I'll just say that this problem had been studied by in a couple papers by Darren and group in France, and they found problems where they could develop exact solutions. And 2 years ago at the APS meeting, I was reading the paper, and the paper by Bickel and Descheveri, and I started to talk to Fernando, my postdoc, about not finding exact solutions to this problem, but might there be similarity solutions that are quite generic? And so we went on a hunt for trying to find solutions to this coupled flow and surfactant problem that had the feature that we didn't care what the initial data was, but we wanted to know at longer times, are there self-similar solutions? And suffice it to say that I'll just skip the details that there are, and I'll just show you the idea of it. And Fernando would explain all the details to you. But imagine you have a surfactant distribution. This is my last slide, by the way, like other than conclusion slide. Imagine I have a surfactant distribution that's sort of located like this localized region. It sets up a velocity field, which is 0 far away, but is moving to the right of it, and moving to the left of this center. And then if you numerically solve this equation, you get a spreading front. It turns out the similarity solution for this problem shows that there's a scaling for surface tension and velocity that maps all of these curves nearly to the same curve, this purple curve at late times. And the similarity solution that you find analytically is the black curve picks it up nearly exactly. So again, the same kind of ideas start to happen, that you can find scalings and reductions through this idea of self-similarity. In this problem, the details are much more complicated because of the two features, the fact that it's Burger's equation and the fact that you're dealing with a complex function. Okay, so I'll skip the last thing and just say I'm glad I had the chance to talk to you. I realize my time is up, but I've shown you a number of different problems, or at least tried to sketch different ideas. Here, there was a common theme of self-similarity, but the beginning of the talk started with some different things that we had been doing at higher Reynolds numbers. And with that, I'll happy to answer some questions.
Thank you so much for the great talk. Anyone from audience, if you have questions, please feel free to just turn on your speakers and speak up or type in the chats, please.
Someone has to ask something. You could ask me what I had for dinner, I suppose.
Hello, it's Richard Brown here.
Hi, Richard.
Hey, I'm from Queensland University of Technology. So very, very nice talk. Thank you so much. It's great to have something that kind of gets down to basics and simplifies many complex realizations of an experiment. But look, my question is, yeah, a lot of people have been thinking about COVID-19 and aerosols in one form or another. Have you done any work on anything along these lines for aerosols themselves, the physics of aerosol formation, agglomeration, growth and decay, and many other, the physics, the problem I suppose with aerosols is that there's so many different aspects of physics involved. There's more than just the, 3 equations like the Navier-Stokes equations. So yeah, just wondering if you have, or if you could speculate a bit about that. Is there anything likely to be self-similar about aerosols?
So I can say we have a different project in my group with a research I work with in Maximus Hertscher, where we look at sprays and the aerosols that are produced in different spray processes. And we understand something about the drop size distribution that comes from that, from first principles. And because the drops are so small because of a novel way that Max makes them, the droplets dry quickly to make powders. And so we have a sort of a research arm and a little technology we're working on that. But with respect to COVID, I guess I can say 2 things. One, I didn't put in the video, but early in COVID, oh, it's embarrassing. I've misspelled respiratory on my slide. Early in COVID, you would read about where do aerosols come from. And my reading of the literature prior to 2020 was that people said the droplets either come from deep in your lung or the upper airway. We all have friends that when they talk to us, spit on us. And so my colleague Manuk Abkarian started to, in his home, actually in a closet, started to image in a dark room with one light and his iPhone, started to image what comes out of your mouth when you're just speaking. And there are lots of small droplets you can see that are likely being formed in your oral cavity and at your lips. And we actually wrote one paper documenting sort of when your lips are wet, as you open your lips, effectively threads being formed. As you breathe out, they stretch the threads and then breaking into droplets of many different sizes. But I haven't looked at all really into any of the details of that process. So it is an interesting question. Of course, people are also looking at how you dry, the role of polymers and mucins in your mouth that might either protect or do something to other things that come out of your mouth. But I haven't looked at any of those details.
Yeah, I'm thinking a little bit about the evolution of aerosols once they get out of your mouth. And the evolution is like really complex, and they're solid as well as liquid particles. And
there's a fair amount in the flu. If I could say, Richard, one other thing, then maybe there is a fair amount done both experimentally and numerically trying to understand something about the droplets after they're formed. And like numerically, people not only trace their trajectories, but try to look at them as they dry. And Eberhard Bodenschatz has a big collaboration and a very nice article, I think in maybe PNAS or Reviews in Modern Physics, one of them, a long review article summarizing some theoretical work, but a lot of experimental work on the aerosol problem. So.
Okay, great. Thank you. And thanks again for your talk. I really appreciated it.
Okay. Well, thank you for the kind words. Azada, over to you. And
if I may, out of curiosity, may I ask, you have at the beginning showed where formation of this bubble streaks in the T-junction flow.
Yeah.
So this way bubble is lighter than the fluid, right? This also depend if you looked at heavier particles or density margin. So what's in terms of the particle properties?
Yeah, so it's a great question. So
the size or the density important?
Yeah, so what matters for this trapping, as far as we can tell, is the density difference between the particle and the fluid. The particle has to be lower density to get trapped inside the regions of vortical flow. And we did some experiments with kind of hollow particles, and we did some try to understand something about the density difference needed for trapping from 3D numerical simulations. But it's a great question, but everything is controlled in this case by the density difference. If the particle is more dense than the surrounding fluid, then as it tries to follow a streamline, if it's moving in a circle, it's like a rock on a string, so it's pushed away from the center of the vortex. The vortex, of course, is being created by the high Reynolds number flow and the geometry, which curves the streamline. And but if the particle density is less than the surrounding fluid, then at least the trajectory is towards the center of the vortex. And I think in our paper, our original paper, in fact, I think we estimated a density difference of, like 0.7 that of the surrounding fluid was sufficient to not only get pushed towards the center of the vortex, but remain trapped as the particles circulating in the vortex breakdown bubble. But that is sort of an open question. Probably we didn't study it in great care, and I haven't seen anyone do that.
Thank you, because I find some relation to the studies where they look at finite size but density matched particles. When they put them in pipes or in small ducts, they kind of accumulate in certain regions of the pipe.
Oh, is that right? I didn't know that.
Yeah, so this is purely now a size effect, so therefore density match. So I was curious whether this is also related to this phenomena.
You could send me a paper on that so I could read it. The way we understood everything we did the trapping required a density difference.
Okay.
And for equal density particles, I think we would have said in our case that we wouldn't have seen trapping, but I should say the dye experiment I showed you is sort of the limit where you're really close to the same density. Effectively the particles are so small they're browning and they leak out slowly. But there, at least for a short time, you see the dye was trapped for at least for a short time.
May I just ask if someone else has another question about the rise of the fluid, the problem you showed. Can we use this to somehow control the rise of fluid? So by changing the geometry, because it does become self-similar in the end. So I was thinking somehow the geometry of that cylinder doesn't really affect the rise. So
Can you what?
So what I'm thinking is, can we actually use this change in geometry to alter the rise of fluid and somehow control it?
That was the thing that this very nice paper in Journal of Fluid Mechanics from David Curé's group, he was probably the first to recognize that, at least for the kinds of geometries he considered, and one is, a cylinder near a plane, if you can see this, or he also was previously considered a wedge-like geometry. Independent of those geometric features, the fluid always rose at a rate proportional to time to the 1/3. And so that was why the suggestion was it was universal. And that's sort of independent of the geometry. What we showed was that the prefactor, which is controlling the rate, that's a weak function of the geometry. But in some sense, I don't think in this case, at least it's not obvious to me, how you could control it with geometry at this scale. It could be that if you maybe were at a smaller scale where other forces come in, what's so-called van der Waals forces or small scale forces, maybe there's something. But at the scale of where gravity matters and viscous effects matter and surface tension matters, it's sort of, I still find it a bit surprising. It's independent of geometry, but that was actually the theme of
that's interesting that geometry doesn't have an effect actually.
It's remarkably weak, which is, I think, really beautiful.
Thanks. Do we have any other questions?
All right.
Okay, then I guess we will thank you for joining us at this time. And thanks a lot for the great talk and wish you a good night.
Well, thank you for having me. I hope one day we
Thank
can
you
meet
very
in
much.
person. So.
Thank you.
Looking
Thank
forward
you.
to it. Thanks. Bye.